seminar series for the semester. We are posting all of these seminars up on the YouTube channel. So if you've missed one or you want to revisit anything, they will be up on the YouTube channel shortly after the seminar ends, and the rest of them are all up and up to date at this stage. Thanks everybody for joining. Yang Yu is joining us from Singapore, so that's where we have the slightly different time for the seminar today to help make that a bit easier. So we're really excited to have him here today. He is a presidential young professor at the National University of Singapore. He's on the early career track at NUS for exceptional young academic talents with great potential to excel. He received his PhD in computer science from UC Berkeley, where he worked with Professor Jim Dummel, who was the former chair of computer science division in the EECS department. Yang Yu's research interests include parallel distributed algorithms, high-performance computing, and machine learning. The focus of his current research is scaling up deep neural networks, training on distributed systems on supercomputers. And in 2017, his team broke the world record of ImageNet training speed. In 2019, his team broke the world record for the BERT training speed. And the BERT training technique has been used by many tech giants like Google, Microsoft, and NVIDIA. His Lars and LAM optimizers are available in the industry benchmark MLPerf. He is a winner of the IPDPS 2015 Best Paper Award, the ICPP 2018 Best Paper Award, the AAAI 2023 Distinguished Paper Award, the ACL 2023 Outstanding Paper Award, and the ACM IEEE George Michael HPC Fellowship. He is a Siebel Scholar and a winner of the Lotfi A. Zadpa Prize. He was nominated by UC Berkeley for the ACM Doctoral Dissertation Award, and he made the Forbes 30 Under 30 Asia list in 2021 and the Forbes 100 Most Influential Chinese in 2023. He won the IEEE CSTC HPC Early Career Research Award for Excellence in High Performance Computing. He is, we're really excited to have him so much. Thank you so much, Yang, for coming and giving the talk. I'll turn it over to you. I'll turn my video off. And again, we're excited about the talk, and thank you so much. I'll stop sharing.
Okay.
You can
Okay.
take it back over.
Thank you.
There you go. Thank you.
Okay. Okay. Hi, Marty, can you see my screen? I just want to
Yes.
confirm, can you see my?
Yes. Yeah, we
Yes.
can see it.
Okay,
Yeah.
great. Thanks so much, Amanda. Thanks for your invitation. Today I'm going to introduce so how can we make AI run faster and more efficient? Firstly, let me show you a figure. So for this figure, the horizontal axis is the timeline. You see, so I just want to show the data from 2016 to 2021. So you see, in these years, we can see we are having better AI models, but our AI models are also becoming larger. So actually in 2016, so the best AI model was ResNet 50. ResNet 50 only has 25 million parameters, roughly 25 M parameters. In the year of 2021, so we have the model like a switch transformer. Switch transformer has 1.6 trillion parameters. So just 5 years, our models are becoming much larger and also more computationally expensive. So that's the level of model we use today, like ChatGPT 5 or ChatGPT 5.5 or 5.4 or Google Gemini or Grok. They use some similar techniques like a mixture of experts as a switch transformer. They have roughly 1 trillion parameters. I mean, our models are getting better, but they are also more expensive to train. It's very hard. So for my research, which is similar to Amanda, is I think for high performance computing. So we want to use the techniques of high performance computing to make the AI models run faster and more efficient. So specifically, so we want to propose to introduce some empirical methods to make AI faster and more efficient. So today I'm going to give you three examples. Firstly is system level techniques like parallel computing, how can we partition the model or the data to different GPU servers or different GPUs? How can we to reduce the communication costs? And the second, I want to introduce some algorithm tricks. By using these tricks, we can make AI run faster and more efficient. And also number three example, I'm going to introduce uh, the optimizer level techniques. By building better optimizers, we can make the AI model converge faster, right? If the AI model can converge 2 times faster, we can cut the GPU cost by 50%. That's very important, eh, because today we have thousands of hundreds of GPUs to train the AI model. It's very expensive. We want to reduce the cost of the GPU budget, right? So without further ado, now let me introduce the first part, system level techniques. Uh, so also, let me show you a figure. In this figure, the horizontal axis is sequence position. The vertical axis is negative log likelihood. Lower is better. So from here, we can see, so with longer sequence, our AI models can give us better results. So that's why today, the sequence length of the AI models are very long. Gemini 1.5 Pro, uh, the sequence length millions of tokens. Cloud 3, 1 million tokens. GPT-5, according to the data from internet, 400K tokens, right? So the best model today, they need to process very long sequences, right? So because long sequence can give us better results, but if the sequence is very long, the memory cost is very high. So here, let me show you some notations. So here, B is the base size, H is a number of heads. So N, small n here is the number of tokens in the input sequence. And the memory cost is order of n square, order of n square for transformer. That means if we have a longer sequence, we have a very high memory cost. It's kind of a quadratic complexity. So here, let me show you some data. So here is for GPT-J. The horizontal axis is a sequence length. The vertical axis is required memory. You see, we have longer sequence and our memory cost is much higher. So a straightforward solution is to do sequence parallelism, right? Because the memory cost is so high, if we just put the whole sequence to each GPU, the GPU will be out of memory, right? We want to avoid out of memory on each GPU. So that's why a straightforward solution is partition the sequence to different GPU devices, right? For example, we have two GPUs, we just partition the sequence to two parts. So that's easy for the implementation of sequence parallelism. However, we have a bigger problem here. So if we just use the straightforward implementation, we partition the sequence to different GPUs, Because for the attention computation, each token needs to do the computation with all other tokens, right? Every token needs to talk to every token. So we need to do all-to-all communication for here. That's a very high overhead. So now let me introduce our solution proposed a few years ago. We firstly propose the ring self-attention. So the idea is to minimize the time for the sequence parallelism, right? And minimizes the training time or communication time, right? We want to do some overlap. So here, let me use a very simple example to visualize this idea. Firstly, we have four GPUs. Assuming we have just four GPUs, but it's the same idea. Even you have 400, 4,000 GPUs, it's the same idea. Here, I just want to make it easy to visualize. I just use four GPUs. So here, B is the base size, S is the sequence. We partition the sequence dimension. H is heads. So we firstly partition the sequence to different GPUs. We know for on every GPU, we have some local tokens, right? And firstly, we do the attention score computation by just use the local tokens. Because the tokens on each GPU, no communication between different GPUs. We just do the local computation firstly. We compute the Q, compute the K, and then we compute the attention score. Right? After we finish the computation for all local tokens, now for each step, we send our old key to our right-hand side neighbor and receive a new key from our left-hand side neighbor, and then we do the computation again. Because now we have a new key, right? New key, we do the computation again. And the next step, we do the same thing. We send our old key to our right-hand side neighbor to receive our new key from our left-hand side neighbor. Everything do the same thing, right? This guy also send our the old key to here and receive a new key from here, right? In this way, after n steps, we can finish everything. So that's the idea for ring self-attention. So for every step, we just transfer the key embeddings and value embeddings. This is a vector, this is also a vector, right? So by doing so, we can reduce the memory cost for training transformer models by a lot. So here's the baseline. So it's order of a small n square. So now big N is number of GPUs, right? You see, we can reduce the memory cost, right? That's the new memory cost. N big N is number of GPUs, right? And also we can make it run faster compared to the naive sequence parallelism. So this is the naive sequence parallelism. They need auto communication. Now for the ring self-attention, so the time just the order of big N. So here the naive or straightforward implementation, the time is order of n squared, right? We can make make the sequence parallelism run faster. We proposed a better sequence parallelism solution. So here are some results. You see, by using the same number of GPUs, Colossal AI here means our implementation. Mectran means just using the tensor parallelism. You see our implementation has a higher performance. Also here, uh, Mectran means just use tensor parallelism. Colossal AI means our secret parallelism implementation we can achieve a higher throughput. And also we can use a longer sequence on the same number of GPUs on the same device, same hardware, right? So I also want uh, to introduce the difference between ring self-attention and the ring or reduce, because ring or reduce was proposed before us. It's for the all reduce operation in training AI models. So here I want to highlight the difference. So the first difference is the ring or reduce. They just aggregate the data, but the ring self-attention, we need to guarantee every query attains all the key values. It's much more complicated. And also, for ring or reduce, it's just a communication operation. But here for the ring self-attention, we need to integrate the communication with the computation. And also we need to do the softmax normalization. It's more complicated. So to our knowledge, the first sequence parallelism solution was proposed by our paper. We published our methods in the year of 2022. These tech giants, they either use our methods or they cited our papers. And for the second part, let me introduce the algorithm level techniques. Uh, for here, let me introduce PAB, Pyramid Attention Broadcast. We want to use PAB to make the video generation model run faster. I mean, for the inference, right? We deploy the video generation model, but the video generation model is very slow. We want to make the video generation model inference faster. So why the video generation models are very slow, like the DIT-based video generation models? So even the model is very small, the number of tokens is very large, right? So for very small video with just 10 seconds, 720p. So even this tiny video can have 1 million tokens, right? So that means video data, they have a lot of tokens. So even for generating this tiny video by a 1 billion model on one H100 GPUs can take us 6 minutes. That's very slow, right? Because this is just a very tiny video and by a very tiny model, right? How about in the future, we need to generate high quality videos and also the length can be several minutes or even hours, right? So that means the speed is very important here. We want to make the video generation models run much faster because it's very slow for today. Now we already have many techniques like low precision, like quantization, like pruning, right? Make the model become some sparsity techniques, right? We already have many techniques, but can we invent some new techniques orthogonal to the existing techniques, it's particularly sparsity techniques or tensor parallelism techniques, right? We want to invent some new techniques, right? Firstly, let me show you our findings in the video generation models, DIT-based model, diffusion-based models. Right? So here, let me show you a figure. So the horizontal axis is the diffusion step. The vertical axis is the difference of the attention between different diffusion steps. We can see something very interesting here. So in the middle of the 70% of the steps, so the attention outputs or attention score are changing very slow, right? You see? So here, the changing very slow, almost no changes. That's our first observation. So the second observation is for these three different kinds of attention blocks, cross attention, the change is very, very minor. Spatial attention is more aggressive, right? So this is almost no change here. It's also minor change, but it's much more aggressive than cross attention. So that means, so the magnitude of the changing, I mean the changing magnitude for different attention blocks, spatial attention, the changes is larger than temporal attention. Temporal attention is larger than cross attention, which means cross attention is the most stable attention block in the 70% of the diffusion steps, right? So by these two observations, now we want to use our findings or observations to design a new algorithm to minimize the computation or to avoid some recomputation. So how can we do that? So firstly, because we know in the middle of the 70% of the diffusion steps, almost no change. How about we can just reuse the spatial attention or temporal attention or cross attention because no change, right? Almost no change or changes are very minor. We do not want to compute the attention again. We just broadcast the attention across different steps, right? Because they almost no change, right? For cross attention, it's so stable, right? We reuse cross attention for 6 times or 7 times, right? For the next 6 steps, for next 7 steps, we can just broadcast the cross attention to the next 6 steps. Right? For temporal attention, maybe we reuse it for twice. For the next steps and also the next step after next step. Right? And for spatial attention, maybe we just reuse it for once because even minor changes, but it's more aggressive than cross attention, right? So you see, the broadcast range for cross attention may be 7 steps. So here's 2 steps. So here's 1 step. It's very like a pyramid, right? I mean, the pyramid here is just the broadcast range. So by doing so, we can avoid a lot of computation, right? So here, which means we run the diffusion model 7 step, we just compute once. So we run for temporal attention, we run the diffusion 3 times, we just compute once. So here we run the diffusion model 2 times, we just compute once, right? That's much more efficient. We can reduce the computation cost by a lot. And so here, you may ask the question, so should we broadcast the attention outputs or the attention score? So here, our decision is we want to broadcast the attention outputs. Why? Because this is much more efficient because we can avoid the key VO vector projection, the position embedding layer norm, right? Because we just need the output, right? We want to make it easier. And actually, there is another advantage of PAB. So for here, we know the sequence length of video data is very long, right? Video data can have millions of tokens. That means we needed to do the sequence parallelism for attaining computation. But because we avoid computation for many steps, right? For these steps, no need sequence parallelism because we do not do any computation for the attention, right? I have no computation for attention score or attention output, no communication for sequence parallelism, right? That means we can also avoid communication by a lot, right? Because the communication is from the sequence parallelism. The sequence parallelism is from the attention computation, right? We avoid the attention computation, we can avoid the sequence parallelism. We avoid the sequence parallelism, then we can avoid the communication cost, right? So another advantage of PAB is we can avoid communication to make it even faster on multiple GPUs, right? So that's why we can achieve a very high speed up for multiple GPUs. So here, let me show you some data. We tried the different open source video generation models like OpenSORA plus Letta. You see, on the same GPUs, for one GPU, we can be 30% faster. On 8 GPUs, we can be 10 times faster because we avoid sequence parallelism, we avoid communication, right? So that's the idea, right? You see, the 10 times speed up, roughly 8 times speed up, roughly 9 times speed up, right? And we make the video generation model run much faster, but we also need to make sure the video quality is the same. You see, almost the same, right? Almost no change in the video qualities, right? We try many benchmarks. We make it faster. Also, no lose in the model quality, right? The model quality, the video quality almost the same. You see more results, right? We make it run faster. We also want to make sure uh, no loss in the model quality, right? Almost the same for the video for the video output by different models, right? So here, let me show you a demo, right? Uh, Now I just want to highlight the difference here. So this is without a PAB. This is with PAB. Very easily we can see this guy is much faster. We generate 5 videos, right? Uh, so firstly, we finish the first one with PAB and finish the second one by PAB. We finish number 3 by PAB. We finish number 4 by PAB and number 5, right? So you see, this guy finished the 5. This guy is still processing the first one, right? That means 5 times speed up, at least 5 times speed up, right? I see. That's why PAB is so efficient. So the takeaway for PAB, the key inside here is we observe the redundancy in the attention computation for the diffusion model. We want to avoid some recomputations, right? We propose the uh, attention broadcast method. Right? We can reuse the attention outputs and also avoid the sequence parallelism. That's why we can get 10 times speed up on multiple GPUs. Uh, so PAB is being used by many tech giants like Meta, Tencent, Alibaba, right? And also we make it open source. So we got, I think, for today, maybe 3,000 GitHub stars, right? So in the final part, let me also introduce the optimizer level techniques. So can we design better optimizers to make the AI models converge faster, right? So if the AI models can converge faster or more scalable, that can be very important because that can reduce the cost, right? So for here, let me firstly briefly introduce the data parallelism. So today we know we often have multiple GPUs or multiple devices, right? We have a bunch of data, or we grab a bunch of data from our training data set, right, for every iteration. And then we, if we just use data parallelism, we partition our a batch of data to different servers, different devices, right? And then on each server or each uh, device, we do local forward propagation and backward propagation. We can get the local gradient, right? Local gradient for server one, local gradient for server two, local gradient for server three. Now we want to compute the average of them, but they are on different servers, right? They are on different devices. So we do all reduce operations uh, to compute the average of all the local gradients. We can get the global gradients, and then we broadcast the global gradients to all servers, right? And then we use the global gradients to update the local weights. That's the idea for data parallelism. So here for data parallelism, if we have more servers, clearly we want a larger byte size. So why larger byte size? So here, let me show you the intuition. So assuming for each server, the best byte size is roughly 500, right? That means we have two servers. We want a base size of 1K. We have four servers or four devices. We want a base size of 2K. And then we have eight servers or eight devices. We want a base size of 4K. By doing so, if we fix number of epochs, we increase base size, we are reducing the number of iterations. So we make a full use of all GPUs, all servers, all devices. At the same time, we can minimize the number of iterations. However, if we increase the base size to very large, the concern here is even we train the same number of epochs, our accuracy is lower. So here, the blue line is the baseline, the black line is library training. You see? So even they train the same number of epochs, so you see library training is not stable and also lower accuracy. So why? There are many different studies for this problem. If you like, you can check the paper on ICLR, like paper this one published in ICLR 2017. So from this study, the author claimed library training is a sharp minimum problem. So what's sharp minimum problem? Let me give you a visualization. So this is flat minimum. So should be the small batch training or the baseline, like base size is 200. So this is a light batch training, like base size is 10K or 20K. So for flat minimum, if we can get a good training accuracy, our testing accuracy should be also very good. But for sharp minimum, even our training accuracy is very good, but our testing accuracy can be very bad. That's the idea for sharp minimum. The the author from this paper, they claim the live batch training is a sharp minimizer problem. So now let me also show you our findings. So we wanted to print out some interesting information for live batch training. Right? So here, how about let me just use AlexNet because it's easy to visualize. AlexNet only has 8 layers. So for each layer of AlexNet, we firstly print out the norm of weights, and then we print out the norm of gradients, and then we compute the ratio between the normal weights and normal gradient. We can see something very interesting. For here, we can see for layer 6, this ratio is over 1000. For layer 1, this ratio is just roughly 6, right? So that means for all the layers, if we use the same lane rate for all the layers, right? For live batch training, layer 6 may need a huge lane rate, but layer 1 may need a very tiny lane rate. That's why we want to introduce the idea of a trust ratio. So what's trust ratio? Because clearly for different layers, they need to different lane rate at runtime. Right? So we need to introduce the idea of trust ratio to get the best lane rate for each layer. So here, how about for each layer and at different iteration, let me introduce the idea of trust ratio and how we use trust ratio to compute the best lane rate for each layer. Right? Right? For each layer, we firstly just compute the gradients. Right? Uh, X here is the data. W is model or the weight, model weights. We compute the gradients, and then we initialize the trust ratio for the number L layer for the iteration T, and then we compute the norm of the weights. And then we compute the norm of the gradients, and also we have layer-wise weight decay. And then we can get our trust ratio. So for here, we can see something very interesting. So we use trust ratio to update the momentum, and then we use momentum to update the weights for different layers. You see, because the trust ratio here is different for different layers, their gradient updating are much different, right? In this way, so each layer can have its unique lane rate or unique model updates. And also, we dynamically compute the trust ratio at the runtime, right? For different iteration, it's also very different. Now, let me give you more information. So this algorithm is named as loss, right? Which means momentum IGD with trust ratio at loss. We know momentum IGD is very efficient, but today we often use Adam for live batch training. Now we want to introduce the trust ratio to Adam. So the difference between momentum IGD and Adam is first moment and second moment. Now we compute the gradients for each layer at each iteration. And then we, just like Adam, we compute the first moment, we compute the second moment. And then we do bias correction for first moment, do bias correction for second moment. Then we initialize trust ratio. Then we compute the norm of the weights, compute the norm of the model updates, right? That's not gradient, but we know in Adam we use this to update the model. Now, same idea, we compute the ratio, the trust ratio, and then we use the model updates with trust ratio to update the weights. Right? So from here, we can see this is element-wise operation. Right? This is also element-wise operation. We give the model element-wise updating and also here layer-wise correction. Right? That's the idea for LAMP. So now let me first issue the results after we use LARS for our library training, and then I want to give an intuition why this works, why this can make library training more efficient. Right? By using LARS, now we can see training the same number of epochs, we increase the base size from 256 to 32K. We can see our method can achieve the same results, same accuracy, even we maximize the base size. We increase base size to 256 to 32K, we can get the same accuracy. By doing so, we can reduce the number of iterations by a lot. Right? So you see, so here, the blue line for base size 500, the red line, the base size is 4K. Right? You see, they can achieve the same accuracy, but by using LARS, we just need maybe 12% of the iterations way much faster, right? Because LARS make library training gets same accuracy or even higher accuracy by running the same number of epochs, right? Here, this guy, they run the same number of epochs, which means the same number of floating point operations. But they almost get same accuracy. Actually, for library training, accuracy is even higher, but much faster. So now let me give you results for training the vision transformer model. Here, the horizontal axis, the number of GPUs, vertical axis is the speed images per second on the same data set for same model. You see, we can almost get a linear acceleration, linear speed up. So now let me explain why Larson lamp works. Firstly, I want to answer the first question. So why Larson lamp can speed up training? So here, let me show you a figure. This figure is a three-dimension figure. So the first dimension is this. So the trust ratio values. The second dimension is here, the number of iterations. The number three dimension actually is here. So how many trust ratios are in this range? How many trust ratios in this range? How many trust ratios are in this range? So we have three dimensions: trust ratio value, iteration ID, and the trust ratio frequency. You see here, very interesting. So in the beginning, for almost all the layers, the trust ratios are tiny, right? That means we have a natural per layer warm-up. So in the beginning, because the training is not stable, we want to be careful. We want to use a very tiny trust ratio dynamically. And then in the middle of training, we can see there are some large trust ratios. Maybe some layers, they are very stable. They need to be very aggressive. But there are some layers, they are vulnerable. They are not stable. They should be careful. And they use small trust ratio. And then go to different iterations. Maybe some layer are here, they go here because for next iteration, they become more stable. And for some layers, they in the beginning, they are very stable, but maybe after some iterations, they become vulnerable. They should use a tiny learning rate, right? From here, we can see because the trust ratio are very smart and dynamic, they can make all the layers maximize the learning rate, right? We can use a very big, very large global learning rate. So that's why we can speed up the training. The first idea why large lamp can speed up training because large lamp can maximize the global learning rate and then trust ratio to control the global learning rate to make all the layers very stable. So, and the second intuition is because the trust ratio actually is the inverse of Lipschitz constant, right? The intuition for trust ratio is the inverse of Lipschitz constants. That means if the optimization landscape is very smooth, that means trust ratio should be very large. We should be learn very fast. We should go very fast. But for other layers, maybe at the same iteration, some layers, their optimization landscape are very sharp, not smooth, and we should be very careful, right? So the trust ratio, just like the inverse of Lipschitz constant, right? Dynamically, they give us the best navigation. You see? So for some layers, even I mean, this guy and this guy, they may in the same iteration, or this guy, they are the same layer for different iterations. So when the optimization is smooth, they should learn faster. When it's not smooth, it should be learn slow, right? The trust ratio is inverse of the Lipschitz constant, right? That's the idea. So we can use the trust ratio to dynamically control the learning speed by the optimization landscape, right? We get the accurate information of the optimization landscape for each layer. So trust ratio can give each layer the best navigation, the best real-time navigation. That's a second benefit of trust ratio, while large lamp can be faster. So here are the applications of LARS. LARS was proposed in the year of 2017. So from the year of 2017 to the year of 2020, so people reduced image training time from 29 hours to 30 seconds. We can see since 2017, almost all the state-of-art training speed were finished by LARS, right? So here is the internet training speed world record by Tencent, Sony, Google, Fujitsu, and Google, right? You see, they all use the LARS to make to break up the image net training speed world record. And also, early this year, Snapchat they use LAM to train their video to train their video generation model Snap Video, right? Because they use LAM, they make some library training more stable and also make it run faster. So also, according to NVIDIA public GitHub, so LAM can be 17 times faster than Adam, right? This is from NVIDIA public GitHub. And also, by June of this year, according to Hugging Face, the most downloaded AI model or most popular AI model was MobileNet V3. This model was trained by LAMP. Yeah. And also Oak Ridge National Lab, their AI drug discovery model, they also use a LAMP, can be 60% the time faster. And also LAMP was part of Microsoft's DeepSpeed. Yeah. So we use a LAMP to reduce bird training time from 3 to 76 minutes. So today, LAM was used by in DeepSpeed, ByteDance, and NVIDIA. So here are the reference papers for this talk. If you like, you can check some of my papers. You can get more information. Okay. So and in recent years, so we implement everything like large LAM, like a sequence parallelism, data parallelism, into one software called AI. So we wanted to build a unified software to train the AI models. It's totally open source. Yeah. So after a few years now, Colossal AI has more than 40,000 stars on GitHub, right? So actually, Colossal AI has more stars on Microsoft DeepSpeed and NVIDIA Mactron. Okay. And also in 2019, so Benjamin Man, who was the first author of GPT-3 and also the co-founder and Anthropic. So he used the LAM actually for the first time to scale transformer extra large to 128 GPUs, right? That's the very early results for using LAM, right? You can check this on internet, right? I mean that means a few years ago, LAM probably is the best method for training large AI models. Right? Okay, I finished. Please let me know if you have any questions.